Well, thank you for inviting me. As you kind of alluded to, this is culminating from PhD research that I did. It was a subject really of my PhD, looking at the volcanic rocks on Skye, principally the extrusive equivalents of the granites, because if you look on Skye, we've got lots and lots of gabbro and lots of basalt. Everybody knows that. We've also got lots of granite, but where is the volcanic rocks that are the equivalent to the granite? And that was my PhD. So it involved a lot of mapping around the area that I'm going to talk about tonight, which is the Kilchrist area. What happened was that I got waylaid with a meteorite ejector layer that we discovered towards the end of the research. So I've finally managed to get this written up now. Hopefully it's going to be published in the journal Volcanica in the next couple of months. We just had the first draft back with minor revisions, so I hope to get it back to them in the next 3 or 4 weeks. The reason that I've put this slide up right at the start really of the talk is because you don't really need to go any further than this. This is the culprit. This is the reason really. The blob that you see in the middle that I'm indicating here, this is mafic magma, which is sitting within silicic magma, in old money acidic magma, more than 65% weight SiO2. So that's the background. And mafic magma, this one probably coming in at about 1100 degrees C. Anhydrous melt, this one maybe 600 to 800 degrees C. This one heats up that one, and there's a vigorous expansion and eruption. And throughout the province that Skye forms, the British Paleocene Igneous Province, this is seen throughout the province. Val Trolls reported on this an awful lot from Rum. I think there was Angus Miller gave a talk to your society about 12 months ago that probably mentioned this. So Val's reported this a lot from Rum. So I'm going to talk a little bit more about this later. So I'll run you through the very quickly the igneous history of Skye. Okay, so a short igneous history of Skye. Okay, so the cause of volcanism on Skye, well, this is been perceived as relating to a mantle plume which ascended onto the base of the then where Skye was, the Skye crust. And a mantle plume is a large blob, anomalous blob of magma, which is believed to have originated from this liquid outer core, lower mantle boundary. And there in the cartoon on the bottom left-hand side, it's that's the way it's envisaged. Comes up through the mantle, and this type of volcanism doesn't occur at plate boundaries. It occurs within plate. So, for example, Hawaii there and Iceland, which is an interesting one because, of course, the plume volcanism that is meant to, of course, the British Paleogene province, so Skye, Egg, Rum, Ardnamurcombe, all of the province down to actually Northern Ireland, Antrim, and Slieve Gillian. This is believed to have been caused by the mantle plume, which is the same plume that is responsible for volcanism in present-day Iceland. So this is within plate volcanism, nothing to do with subduction. Although the interesting thing is that Iceland volcanism, as you're probably aware, Iceland sits on the mid-ocean ridge, but it's also coincident with the path of the mantle plume. So you've got two bites of the cherry really there. So what I've tried to show here is that these are the Canary Islands, of course, quite topical at the moment because we've got eruptions in La Palma last year, which have, in fact, I think they might still have been ongoing until very recently. And the idea here is that the Fuerteventura to the east, this is the oldest of the Canary Islands, and we've got volcanism on La Palma at the moment, and El Hierro has been quite recent volcanism. So the actual mantle plume is static, and the plate on the screen here is moving to the right-hand side, producing these islands. Exactly the same thing happening with Hawaii. So this is this hotspot plume type volcanism. And this is what was responsible for volcanism on the Isle of Skye. Okay, well, the start of volcanism on Skye, this is an interesting one because the basalts on Skye have not been absolutely dated geochronology very well indeed. In fact, it's layers that are within the basalt on northern Skye which have been dated. So geochronology for Skye with relation to basalts is quite poorly understood. In the Cretaceous, the mantle plume is thought to have caused uplift, and then there would have been erosion of the land surface. So essentially, the first volcanic eruptions took place over what is described as a largely kind of penoplaned land surface with some relief. And you can see in the top right hand picture here, we're actually, Portree is just out of the shot to the left, so the capital of Skye there. And what we've got is that we've got Jurassic sedimentary rocks with basalt flows on the top here. And some of the very first eruptions were considered to have taken place in water. It's not specified whether it's seawater or whether it's inland type of lakes, but erupted into water. And on the bottom right-hand side here, what we've got is that we've got some claggy Jurassic sedimentary rock with the first basalt being erupted. This is just north of Portree, round about this type of area here, just on the coast. Then if we go down to, Portree here, into a place called Camas Ban, what we see is that we see some what are known as Palagonite tuffs, which I'm pointing to there. And this is basalt which has been erupted into seawater. And what you've got is that you've got the meeting of very, very rapidly chilled basalt. So you've got glass, and then it alters to form this product called Palagonite. So this is known as a Palagonite tuff. Now, if we look to the southeast the southwest of Skye, to the island of Canna, the lavas which are on Canna are considered to form part of the main Skye lava series, and they have been dated, and they've been dated, as you can see there, at around about 60 million years, give or take this margin of error. So this is really the only concrete date for the lavas, because these are considered to be part of the Skye main lava series. Now, when we were doing the research on the meteorite ejector layer, this locality is just coming out of Broadford. This is a Neolithic burial ground, the chambered cairn, and within what we considered to be an ejector layer, meteorite ejector layer, we found clasts of basalt which we had dated at this date 61.5. There's a big margin of error here, but this was on argon. So granted, not a particularly brilliant date. So you could argue, well, maybe this is up to 62 million years of age, or down as low as maybe 61 million years of age. So this could be the oldest igneous rock reported from Skye. Well, certainly it's the oldest one I know of so far. I'm calling it an igneous rock because, of course, it could be an intrusive igneous rock which has chilled at the margin of an intrusion so as to resemble a basalt. It doesn't necessarily need to be part of a basaltic lava flow. This was another site which was our first meteorite site, Ejector Layer site, but it is beneath lavas which are on the Strathayed Peninsula, and these lavas flow in towards this area, Camasunri Bay. There's some members of the Aberdeen Geological Society looking at the Ejector Layer at Site 1, immediately beneath the oldest lavas on the Strathayed Peninsula, sandwiched between an intrusive sill, and you can't see it here, but they are on Jurassic sedimentary rocks. If we then move to the northwest of the Cuillins at a place called Fion Corrie, this was my second research area on my PhD. What I did was I was looking at this fantastic volcanic deposit. It's called a lava-like ignimbrite. Now, this is the hottest eruptive product that we know of. Never been witnessed before, this type of eruption, a lava-like ignimbrite. And as the name suggests, the deposit looks like lava, but often it's got small clasts in it. And if you geochemically check it as you move up towards younger parts of the deposit, chemically it's not all the same, which of course it would be if it was a lava. The fascinating thing here, which my colleague, PhD supervisor Davy Brown is looking at, around this area, we found a mineral which is known as brownleite. The closest match, rather, I should say, we could get to brownleite was this mineral here, where my colleague's standing, and this has only ever been found as a dust particle trailing a comet. And that was found in 2008. This is immediately beneath this lava-like ignimbrite once you strip out sills and these dike-like features. So there's a lot of intrusions here. If you strip them out, this would have been beneath this lava-like ignimbrite. And that's what it looks like up close. It resembles almost like a flow-banded lava. And the type of eruption that would produce this is considered to be a low boil-over eruption, because to get it that hot, maybe 1250, 1300 degrees C, you need it to be you can't have a Plinian column because it would then cool down rapidly. You need to maintain the heat. So lava-like ignimbrite. So as I was mentioning to you, is around about this time, so that was those lava-like ignimbrites of 60 million years of age. Around that time, we've got these lavas which are flowing down in towards Camasunri Bay. And this is North Skye. And the reason I put this in, it's a really interesting photograph. You can probably see where I'm picking out a fault trace there, and you'll see a red layer and an amber layer here, and there's the red layer and the amber layer again there, and it's offset. Now, the interesting thing is that the red layer, as you probably know, is called a red bowl, and this represents a break in time between successive lava flows. So here's a lava flow, there's a red bowl, and there's another lava flow. And these bowls take hundreds to thousands of years to form. So there were definitely breaks in time between the various different lava flows. This orange or buff colored, if you like, layer here, this is an example of a ash that fell down on top of the previous lava flow. So this is a full deposit. So you have a full deposit here, and you have a paleosol there. And this is very often seen in Skye. Next we move to the Cuillin. The heart here, the hearth would be a good word, of a remnant magma chamber. phenomenal, really. It extends 15 kilometers in depth, the geophysics would suggest. And the Cuillins were formed as a series of these cone sheets. So magma ascends up and you have these sheets from a single point source. It looked like an ice cream cone, like a cornetto, if you like. Then more magma is pushed up the middle, more and more and more. So the oldest cone sheet is to the margins and the youngest sheet is to the center. And the oldest part of the Cuillins is on the margins, quite close to Camassoonry, around about here where the little arrow is. And this is 58.91 million years of age. And this is considered to be a pretty reliable date. Elsewhere, if you go back to where I was saying at Fion Corrie, so Fion Corrie, I'll just flick it back quickly, northwest margin of the Cuillins. Where I am here on this slide is Skye, I can't pronounce it, Skye Thulm. So that's it. And there's clear evidence there that volcanic rock, earlier volcanic rock, which we think is part of that lava-like ignimbrite group, has been shunted up by intruding gabbro. And it's been deformed and twisted by the gabbro. Of course, over Skye and throughout the Hebridean province, the dikes that you see, there are millions of these dikes associated with North Atlantic opening. And the regional dike swarm, rather like a swarm of bees, is, as you can see on the map of Skye, the bottom left here, it's orientated broadly northwest, north-northwest. And the dikes that we see on Skye are in various thicknesses. I mean, there's a group of students up there on the top left, that dike maybe, I don't know, 10 meters across. I've seen them around Kilchrist, 40, 50 meters across, micro gabbro dikes, whereas to the right-hand side, much, much thinner. And of course, what these dikes represent is that where you have the crust is being ripped open with the opening of the North Atlantic, magma is coming up, injecting through these fractures and then solidifying. So it's actually causing crustal extension. And a really interesting thing on the Isle of Skye is that the amount of crustal extension that you get around the Cuillin, particularly around Camassoonry, is up to about 25%, where elsewhere away from the Cuillin, maybe 2 to 3% around Broadford. This is a date 57.5 million years around Strathnacritic, which is not considered to be a reliable date. And there's another group at the moment, which I spoke to one of the workers from this group. They are doing lots of geochronology on Skye at the moment. The Western and Eastern Red Hills are being redated and the Skye lavas are being dated. So hopefully in the not too distant future, a paper will be written where we can get a real nail down the geochronology of Skye very accurately. But this particular date of this area here, Strathnacritic SNCC, which comprises granites and there's some pyroclastic rocks there, is not really considered reliable, this date on the granites. Then we move to look at the Western Red Hills generally. So these beautiful Western Red Hills, the granite hills on Skye, so-called red hills because at sunset they're said to kind of glow a pinkish. That's if it's not a rainy day. If the sun is out, due to the mineral orthoclase, which is this pinkish alkali feldspar. So the Western Red Hills Centre is quite extensive, about 35 kilometres area, and it also it encompasses 10 granites, and dates on those granites, particularly the Loch Anort granite, they are going to be new dates published quite shortly. the margin of error of kind of 2 million years, which is not particularly reliable. Also, you might notice down here on this map, you've got this area Z here, which I will talk about later. These are actually pyroclastic rocks which originated at Kilchrist. So I'm going to talk about those later on in the talk. This is a really interesting one. This is an area that we found on a PhD research at Mole here. Now, these are ignimbrites. So just to explain, an ignimbrite is the product of a pyroclastic density current, a pyroclastic flow. And to be an ignimbrite, you have to be produced by a pyroclastic flow, and you have to be rich in pumice, ash, or glass shards. And this is an ignimbrite that we found slap bang in the middle of the Western Red Hills. So it's younger than the Western Red Hills, and it's in a stream section around Mole. And we've had this dated at, this is 57.1 million years. And don't know of any other period of volcanism on Skye which is of that age. It's too young to be associated with the square of egg, which it would have been wonderful if it had have been, because you probably heard that recently the square of egg has been linked with the Western Red Hills as originating of the Western Red Hills on Skye. In fact, Davey there, he wrote the first paper on it. And recently Valtroll's written a second paper on it. So yeah, these deposits can't be associated with the Skye, which is unfortunate. We don't know where they're from. So then we look at the Eastern Red Hills, and the Eastern Red Hills are composed of these granitic centres, and the area that I'm going to concentrate on mainly on this talk is this area around Kilchrist. But we've got granites here forming the Bendacalic centre, pyroclastic rocks fringing these granites. This is what I'll be talking about tonight. And really interestingly, we've got this dolostone, so magnesium carbonate everywhere, apart from this kind of area, which is granite. So we've got granite intruding into dolostone. But you look at this picture to start off with and you think, oh, that's just a rounded granite hill. Yeah, so what, really boring. And then you look and you see that there is this section here. These are pyroclastic rocks that I'll talk about tonight, which are older than the granite because the granite is intruded into them at a later date. I'm sure John will know a lot more about this than me, but this is a diagram which has come from the recent Stuart Archer paper describing what Skye looked like in Middle Jurassic times, with the brown areas are land masses, and then we've got these basins, the Sea of Hebrides basin and the Inner Hebridean basin. So kind of Jurassic time, we've got these lots and lots of fossils covered by sea, and we get the ammonites, and I think recently Stegosaurus has been found on, I think, Egg and on northern Skye, and of course up at Duntullen there's the sauropods, so lots of fossils in the Jurassic. And as I mentioned, in the Cretaceous we've got this uplift from the mantle plume, and then we've got planing off, we've got erosion. So the geological setting pre-Eastern Red Hills intrusion, let's have a look and see what I think it might look like. So what we had is that we had the Cuillin here, which I've mentioned, are extending to 15 kilometers depth. The Western Red Hills here, these extend, geophysics would suggest, to about 3 kilometers depth. There was earlier basalts here which flowed towards Camasunary Bay, and they are cut by the Cuillin and the Western Red Hills. So the lavas are older. We've got this intrusive relationship. There's also a fault here, a large fault, which is known as the Camassoonry fault, which you've probably heard of. It's an extensional fault. You see the teeth are on the right-hand side here. So it's an extensional fault. And interestingly, we've also got a major Moine-related structure here, which is the thrust fault. And this forms part of the Kishorn Thrust. Now, this is important because the Kishorn Thrust thrusts older Torridonian sandstone over younger dolostone. So the older sandstone in brown here, marked Tor, and the Canberra Ordovician CO, dolostone, the blue. Now, all the way across all of the eruptive units that I've mapped and I'll talk about tonight, within the ignimbrites, I found clasts of Torridonian sandstone and dolostone. So quite clearly it was near the surface when pyroclastic flows flowed over them. Another really enigmatic thing here. Look at this, Lewisian gneiss. What is that doing there? I mean, that could have been thrust up with this Kishorn thrust. So you've got overthrusting because, of course, the Lewisian would have been beneath the Torridonian. It's older, it's Archean in age. So you've got this kind of setting where you've got a Moine-related large thrust and you've got a Jurassic fault, which is the large Camassoonry Bay fault. So this is extensional and the Kishorn thrust is compressional. And to the northwest of the screen here, you've got a brick wall, which is 15 kilometers deep at the south and 3 kilometers deep where the granite is. So it's playing the part of a barrier before we've even had any eruptions. This is the Kishorn Thrust, just to show you. So in the area, what you've got is that you've got the older sandstone and the younger dolostone. So here the sandstone is shown in this kind of orange and then the dolostone in the blue. So I just mentioned about the Camassoonry Skerryvore, it's called, fault, and it goes an awful long way. Look at this. Okay, so this is Skye. This is the Camassoonry fault. All the way down here. Very large fault. It actually goes between Egg here and this is Rum out to sea. I'll go back to the previous slide. So this is a extensional fault. This is interesting. This is a BGS map showing it as a reverse fault. Well, you can't have it both ways. It's either an extensional fault or it's a compressional fault. And what is really interesting is that if you go down to this region that I'm showing here on the beach, you'll see Paleocene dikes which have been faulted out. So the dikes are there in situ on both sides of the fault trace, but they don't span the beach. So that fault, the Camassoonry Skerryvore fault, must have been active after the Paleocene dikes were intruded. So in other words, the Camassoonry Skerryvore fault at this location was active during the Paleocene, and it didn't cease being active in the middle late Jurassic. The same thing is reported from faults on Rase, I believe, by Rob Butler, has found the same things, that dikes have been faulted out across Jurassic faults on Rase. So you're getting the idea here that you have got extensional faults perhaps which are active still, or faults which are active still during the Paleocene. However, could they be compressional faults, reactivated normal faults? Most authorities suggest that it's not, it's an extensional fault, and this is not a favoured view. So there, as I've showed you, the fault goes out an awful long way. And there's a dike. on way to Camasunri Bay, very wide dike. Okay, so if we look at the geophysical evidence, this is quite interesting. We look at this diagram. This is from the 1970s, and this was done by a gravimeter, and you get what are known as positive Bouger anomalies on this. So this is what these little contours with the numbers are. Now, a Bouger anomaly, that's the difference between the expected value of gravity when you take into account the latitude and the longitude and the altitude of where you're surveying and the actual value that you get. And what this diagram is showing you is that at depth, there is a dense solidified magma body. And there's two sets of workers' takes on what the Cuillin might look like subsurface. This is a Butler and Hutton paper, and this is from 1994, and this is a 1973 idea. Look how deep it extends, as I was saying, 15 kilometers. Then if we look at the next diagram, this is aeromagnetic survey. And this measures the intensity of the geomagnetic field. And what it does is it shows the spatial distribution of magnetic minerals. So the main one, as we know, is magnetite. So where is the magnetite? And this is a survey of the Cuillin's Western and Eastern Red Hills. And this is the area that I'm going to come back later. So dense magmatic bodies beneath all of this area. So against this geological backdrop, what we've got before we start our eruptions is we've got a solid barrier to the north, which is the Cuillin, 15 kilometers deep, Western Red Hills 3K deep. We've got contemporaneous crustal extension, North Atlantic related, I guess, question mark. We've got dikes, and we've also got the Camasunri fault, which is probably, together with the Rasay faults, active at that stage. And this is giving you space to accommodate a growing caldera. Magma can pour into this. And then you've got the Moine-related Kishorn Thrust, so potentially a conduit for your magma. So I put in at the bottom, it's probably pretty bad with what's going to happen to the UK on Friday night, the perfect geological storm. So sorry about that. This is the extent of the caldera that I'm talking about. Compasses the Eastern Red Hills. So this is what I'm going to talk about now. I mentioned these anomalies here to the south, and what I would like to draw your attention to at this point is this marked COR. These are the enigmatic composite sills on Skye, sills which have got basic margins and rhyolitic cores, and they're 80-90 meters thick, some of them. Huge magma conduits. Why are they there? I'm going to introduce this Kilchrist volcanic formation now. And notice that it extends up here, marked KVF. And this is what I spoke about a minute ago. This is this, sorry, just go back a second. This is this area marked Z, previously called a pyroclastic breccia, where gas has streamed from depth and is said to have broken up the rock by a process of gas streaming. But I hope to show you that this is not possible, because not with the deposits that we got. So let's look at the evidence. Well, this is the Eastern Red Hills, and this I showed a minute ago. This is the old priest's house, actually, the old manse, and it's built on dolostone, surrounded by granite, which is very, very close to the surface in place. I mean, it's at the surface here, but where the dolostone is, some places only 3 or 4 meters below the dolostone. So I'm going to talk about a ring dike, and have we got any evidence of a ring dike at Kilchrist which could perhaps accommodate a caldera? So the idea, as you probably know with ring dikes, is you get an ascending body of magma, and what happens is that they start to the crust starts to extend and fracture, and what you do is that you'll get an outline, kind of like you get a circular fault at the surface, and magma can come up the side of the fault, and it starts to produce this kind of circular ring dike. And then in time, what can happen is with evacuation of that magma, the central portion drops and you get a huge eruption, and this is how you can produce a caldera. Do we see this in Skye? Well, if we look here at the purple area, this is known as the Kilchrist hybrid ring dike, and it's been known for years. The northern section of it is presumably been destroyed by intrusion of later granite, but we have pretty good representation of a mixed magma ring dike. And the interesting thing is that the volcanic rocks actually are all contained within this ring dike. Outside of the ring dike, see, this is all dolostone here, whereas within here, this mauve is lava, and the blue and the yellow and the both shades of green, these are all ignimbrites. So all of the pyroclastic rocks are contained within this ring dike. So what I tried to do was to make some sense of this kind of absolute mess and think, right, okay, can we figure out, does it represent any eruptions? Can I put it into some kind of order? That involved logging. So running out a 75-metre tape up the stream sections, there's numerous stream sections at Kilchrist, and literally recording on a centimetre by centimetre scale how the rocks changed and what was the type of rocks that you saw. And from that, to try and figure out, could we determine anything from the eruptions? So this is the map, the full map, my map of Kilchrist, and these numbers here, these are the log sections that I did. So around this area and all the way around the south, there's 18 logs that I put in right the way around to try and reconstruct these eruptions. And I managed to find 4 distinct stages of eruption very broadly. I mean, this ones here are to the west of the granite. It's these ones here, and these ones are to the south of the granite along here. And I mentioned I had 4 stages, basically: the green and the blue, stage 1, lava, stage 2, stage 3, yellow, which is ignimbrites, loss of ignimbrites, stage 4, blues and the greens. You notice on logs, the more it comes out, the coarser it is. So it's very coarse. This is the collapse stage of the caldera. And then this stage, marked resurgence, is when the granite intrudes. So what were the first eruptions like? Well, this is a kind of cartoon of how we envisaged the first eruptions. And there were ignimbrites which were produced, and they were produced as a result of eruptions and pyroclastic flows, density currents, call them what you will, but sweeping down the topography. And we started initially to start to form this ring dike, the Kilchrist ring dike. And we see right at the bottom of this stream section, we start getting ignimbrites which have got clasts in them. And we can also get some breccias, which is to say they've got much bigger clasts in them. So quite variable energy output. Now you might say, well, how do you know that they were the first eruptions? Have you got the land surface onto which they flowed? And the answer is no, we don't. There could have been eruptions before this, and where everything's floundered and collapsed within that ring dike, there could have been earlier eruptions we don't know of. So we don't have a paleo surface on which this started. This is just the first volcanic rocks that we see on top of dolostone country rock. So the next one, the stage 2, this is the lavas, the effusive volcanism. And in the stream sections, we see lots of these amygdales, we see basalt. And the idea on Skye generally is that kind of lava flows were fed from fissure type eruptions, dike eruptions. This, of course, is quite controversial because I don't think I've ever seen anywhere on Skye where you can unequivocally see a dike feeding a lava flow. We've never seen this, but this is the perceived idea of how lavas were fed. They were formed as a result of being fed by fissures. And in between the lavas, as I showed you on an earlier photo, we have these paleosols, you see. So this is a break between two flows, one flow and another flow. We've got these paleosols. This again is that picture shown. So this is the paleosols that we see on North Skye. The main high temperature eruptive phase is our stage 3, and this is where it all starts going a little bit crazy. Volcano tectonic faulting, so we get block faulting in the whole area, and we get very, very hot ignimbrites produced after the lavas. And these ignimbrites are fed via fissures. So here's an example along 2 stream sections of large-scale faults. One rock type here on the left, which is a breccia, and this is a welded ignimbrite on the right-hand side. And there's the fault right the way down here. Again here with my colleague standing there, he's looking at a full deposit on this side and a breccia on that side of the stream. And in virtually all the stream sections you see, there are different rock types on adjacent banks of the stream. So these streams are marking quite large faults which were produced during this caldera growth and collapse phases. And you can see here all the way around the area randomly orientated faults. Within an outer caldera margin, so this is the extent of the caldera, and within an inner margin, lots of different faults. Another thing that's really interesting is that this stage 3 eruptions, the very high temperature eruptions, some of the magma exploited fractures which had previously been exploited by dikes. This is a dike. This is an ignimbrite, and slap bang between the two on the same trend, we've got this fissure, which has got it's expanded tuff within the fissure. So this is silicic magma, which is expanding and desperately trying to get to the surface. And it's actually exploited a weakness, which was first exploited by this dike. I mentioned at the start, lots and lots and lots of evidence of magma mixing throughout all of the eruptions. And this little photograph shows have basically got, see these lath-like plagioclases? This is basaltic in composition. The margins of it are very wavy. That means that it must have been molten or at least plastic when it was intruded into this host, which is much lower temperature. So hot comes into cold, as I said at the start, or relatively cold, cooler, maybe 1200 degrees against 6 to 8. And what happens is that there is this vigorous mixing, you get expansion, over pressurization, and this is when you're going to get an eruption. And this magma mixing has been cited numerous times in the literature as the eruption trigger for large-scale eruptions. And there's lots and lots of evidence of it throughout, as I suggested to you. This is where hot magma has come in and it's actually resorbed this quartz. It's partially melted the quartz, it was so hot. We've got here a piece of basalt which has now been chloratized as a result of later passage of fluids through it. And you can almost get the idea that it's a really random shaped basalt blob, which is very hot. And again, it's stuck in the middle of this silicic magma, which was relatively cooler. This is another, what we call mafic enclave. So a blob of magma. Ignore these. This is where we lasered it. So these are laser marks we made. This is the equivalent, I guess, of a granitic host. So a granitic host in a basaltic blob within it. Totally different in chemistry and different in temperature. This is the trigger. These lava-like ignimbrites at stage 3, the very, very hot ones. This is an example of a lava-like ignimbrite. This beautiful fabric running through it, really intensely folded. Elsewhere in the world, we see this if we go to Northwest America, for example. These are very recent. These are about 8 million years of age. And this is from a famous area known as Gray's Landing in Idaho. And these cliffs, this is lava-like ignimbrite, 70 meters thick. And that's what it looks like. Wild patterns, absolutely beautiful. So this here, modern one, relatively modern one, at 8 million years, it's the same rock as this that we see in an ancient caldera, lava-like ignimbrites. Now the fissures that fed these stage 3 pyroclastic density currents, there's an example here, these vertical kind of fissures here. And in very close proximity to the fissure, so there's the fissure there, the dark brown one, in very close proximity, in fact here, literally a few meters away, you get ignimbrite. And this is partially welded ignimbrite in the stream sections. Top right-hand picture, there's the suspects again, the little black blebs. This is the mafic lava stuck in a silicic host, hot, cooler, and they're throughout all of the eruptions. So these fissures, magma ascended, it expanded, and then it started to produce pyroclastic density currents, which fed these kind of areas and deposited these rocks. We see it elsewhere in other stream sections. This is a large, tough filled fissure in this region. This is a stream section, so there's the tough filled fissure, and very, very close to it is lava-like ignimbrite, which is here. So you've got, this is the feeders for within the caldera. Then we have the stage 4, which is when the caldera collapses and we get the catastrophic type of eruptions, we get the collapse. And also at this stage, this is where we get a local granite starts to intrude, which is known as the Benenduic granite. And this magma, which has supplied all of these eruptions, is ascending parallel to this Moine-related Kishorn Thrust zone. And I mentioned to you about these composite sills. There they are. They too can be feeding this caldera. Isolated out here, these composite sills. And on this collapse stage where the caldera collapses, we get these large blocks, and at Kilchrist they're up to 1 meter across, some of them. And the crags, these are formed of breccias, and I've got 2 different shades of green here, and the dark green is the coarser blocks. So that's basically greater than 256 millimeters across, and the lighter color is between 64 and 256 mils, so smaller blocks than large blocks. And if you look right the way up to the granite, you've got these breccias, and there's my colleague here, and you can see that there's quite decent sized blocks which are within this deposit, and this is on Meal Corrie Forsed. This is one of the large crags. After this, we had intrusion of the granite. This was the Ben Nekhalik Centre, and the Eastern Red Hills resurged through the collapsed caldera. And there's the Eastern Red Hills there. So within the caldera elsewhere, we have evidence of lavas on this peak, which are right on the top of the granite peak, Ben Necro, and they're highly likely to be our stage 2 basalt flows. They've been jacked up. They're earlier basalts which have been jacked up by later granite intruding. And I'm going to draw your attention here to this KVF yet again. Notice that it's KVF stands for Kilchrist Volcanic Formation, this term we've used for our eruption sequence. And we found eruption sequence 3 and 4 from here, right the way over here, actually outside the outer caldera margin. And I mentioned earlier about the fact that it had earlier been classified as gas streaming from depth through gabbroic rocks and this was a concept that was used I think in the 40s through to the 60s, where you had blocks which are broken up as a result of gas streaming. However, at this area we found, you probably know these things, accretion-rich lapilli. Now, they are produced as a result of pellets which are falling out of ash clouds and pyroclastic density currents. And they grow in the cloud and then they drop down into the underlying density currents. And these are these little accretion-rich lapilli. So we found them here. Now, you cannot produce this as a result of gas streaming because it's a completely different process. This is produced from a cloud above, not gas streaming from below. And we found them here at Kilchrist, the same accretion-rich lapilli. Similarly, these ignimbrite deposits, this is found here at Kilchrist, found here at this is known as Belig, a peak called Belig. Notice that these are completely different rock types. So it's not all gas streamed and broken up one rock type. These have been part of a pyroclastic flow which originated from here, same as these ones. One of the things that was absolutely fascinating that we realized was I got the rocks dated from stage 3, the very hot stage. And what was fascinating was that the zircons that within those ignimbrites came back as being 56.15, give or take that margin of error. This is exactly on a time in Earth's history known as the Paleocene-Eocene Thermal Maximum. A bit of a mouthful, but this is when global temperatures spiked, sea temperatures 8 to 9 degrees, and atmospheric temperatures perhaps by 5 to 8 degrees. And you can see this is the spike here. So sea surface temperature at the top, there's the spike. Ice-free deep ocean temperature, there's the spike then. And this was at the meridian, the temperature gradient, and there's a spike there at exactly that age. Now, this is, to the best of my knowledge, the first occurrence within the British Paleocene-Eocene Igneous Province of large-scale eruptions occurring precisely on the PETM. There was a paper a couple of years ago, which you're probably aware of, that Val Troll reported and worked on increased the work that David Brown had done on the Square of Egg, provenance in it to the Western Red Hills on Skye. The trouble is, you see, is that the Square of Egg is 58 million years of age. So that's been dated at 58. So that's older than the PETM. These eruptions are bang on the PETM. So how did potentially the atmosphere, these eruptions, increase atmospheric temperatures? Well, there's an awful lot of dolostone which was intruded by granite and by basaltic dikes. Not only was there dolostone, there was organic Jurassic sediments. And actually, for every kilo of dolostone that you destroy by direct melting, you'll put 239 grams of CO2 into the atmosphere. So potentially, if we look at the area, the caldera, that, as I'll show you in a minute, there's an awful lot of dolostone. Now I'm standing on a peak that some of you might have been on before, which is known as a Ben Swardow. And we went up to the summit of Ben Swardow and noticed there was a dike there, and within the dike there were these granite xenoliths, cricket ball sized granite xenoliths. We had the zircons in those dated at 56.25. So 500,000 years before the stage 3 eruptions, there was a large body of granite magma beneath a limestone peak, Ben Swardow. There's Ben Swardow. So incorporated within a dike, granitic xenoliths have been intruded into that dike. Now, it's not to say that the magma chamber was directly below Ben Swardow, because, you know, as you know, these days, the idea of a kind of a magma chamber straight below the caldera is kind of a little bit old hat. The idea these days is that you've got dikes and sills feeding a kind of a system. And I think recently, kind of Craig McGee has said that in the Karoo in Africa, you know, you've got sills which have there's been magma transport in sills that's gone on for hundreds of kilometers. So, you know, lateral magma transport is well known. So there wouldn't necessarily have to be a granite body directly under Ben Swardow. But we know that there was granite in the area, because this is all granite here, you see. And it's jacked up and intruded this dolostone. But look at the amount of dolostone here. So we know that there is granite in xenoliths there. And that granite xenoliths is 500,000 years older than our stage 3. So all this granite here, this is intruding into this dolostone. We've got loads of northwest southeast trending dikes, which is intruding into the dolostone. We got Jurassic sedimentary rocks, organic ones here, which are being cooked up by composite sills. We got very hot gabbro there, which is cooking up the dolostone. And we've got Jurassic here, which is being cooked up by granite. So there's potential here for an awful lot of CO2 to be released into the atmosphere. Back of a cigarette paper calculations, well, it was a little bit more than that. If we had a 30% loss of the cumulative dolostone thickness, which actually is 500 plus meters there, we would put 3.9 gigatons of CO2 into the atmosphere from this Kilchrist Caldera. A 50% loss could result in 5.2, an 80% loss. And you could account for this because you're thickening with the footwall. So when the Kishorn Thrust is produced, Moine-related Kishorn Thrust, you're going to have thickening of the footwall as a result of thrusting. So that is plausible. You could put 8.5 gigatons flux, and that is, you know, the kind of 6.3. That was the anthropogenic CO2 emissions in the late 20th century. Way more than that now. But, you know, this is a pretty significant kind of event, and could have accounted for North Atlantic atmospheric warming on the PETM. So, in conclusion with this, the silicic volcanic rocks, these ignimbrites, in the last few years, we're really beginning to realise how important they are. Bob Gooddays recently talked about lava-like ignimbrites in the Caldera on Arran. Davy Brown, Val Troll, the square of egg, as I've mentioned. I mean, that square of egg, if that did come from the Western Red Hills, the run out on that is maybe, what, 40, 50 kilometres. Very, very large. And these are almost like glass fusing eruptions. So big, big eruptions. The Skye stuff, which I've spoken about tonight, and also ignimbrites we described from Strathair Peninsula 2012. Rum, of course, Val Troll, his most recent paper, 2020, you're probably aware that there's a fault that runs north-south right the way through Rum, and he's suggesting that the Rum igneous episode, magma fed that episode through that fault, very similar to what we're saying on Skye, that the faults acted as conduits for the magma. And of course, on Mull, there's ignimbrites there with the lock bar, ring dike and associated ignimbrites. So silicic volcanic rocks are starting to become very important in the British Paleogene Igneous Province, whereas before all of the research centred around gabbro and basalts, we're now beginning to learn where the pyroclastic equivalence of the granite is, and they're there all right. Anyway, thank you for listening, and this was back in October in the middle of the Cuillin. So thank you very much for your attention. I hope I didn't go on too long.